Hey, I'm Dr. T, and welcome to my office. Let's talk a little bit about the origins of chemistry. We're going to be studying chemistry for a while, so it's a good idea to know where on earth the thing came from. And I guess first, before we talk about that, we need to talk about what is chemistry. So chemistry is the study of chemicals, as the name explicitly states. You know, chemicals, chem, history, that's the study of, along with a couple other endings that mean the same. Now, what's a chemical? A chemical is going to be anything made up of atoms, which is a great way of broadly defining something so that its meaning includes basically everything. In general, what we're going to be looking at is the building blocks of the stuff that we deal with. By understanding how stuff is built, what goes into it, how those building blocks interact with each other, we can understand a lot about the stuff we have and potentially ways to improve it. There's a German chemical company, it's an old one, BASF. Back in the 90s, they used to run a bunch of ads that all ended with the tagline, "We don't make the things you buy, we make the things you buy better." And the general idea is that by understanding how and what things are doing, you can understand how to make them better and how to do better things with it. And that's been a goal for quite a long time. The origins of chemistry really branch into three proto-scientific areas. The first is the apothecary. Now, that actually still holds on to a limited degree, really in the pharmacies that we use. If you go over to Europe, a lot of the pharmacies are actually called apothecaries, depending on where you're at, of course. The goal of apothecary is to take natural substances, plants, fungus, animal products, etc., and use them in a way that cures disease and makes people healthier. And that's still a goal of chemistry. Medicinal chemistry is a major branch. The next area was metallurgy, and metallurgy has stayed its own discrete field, although it's heavily influenced chemistry, and it is a true science in its own right today. Metallurgy is the study of metals, understanding how to take them from their ores, which are rocks, and do chemistry on them in order to make a usable metal, things that you can do to it, such as mixing it, heating, cooling, etc., that will allow you to make a more useful metal. And that influenced chemistry a lot. There's a lot of chemistry going on in metallurgy. It's basically a field of chemistry, although it's usually hanging out with the engineers. And all of that learning applied to a lot of things that have nothing to do with metals, but they have everything to do with what's going on with the metals. The third and most famous one is alchemy, and by famous, I mean infamous. Alchemy was one of those interesting fields. It had a lot of the proto-science in it, but it also had a lot of metaphysics. And metaphysics and science are not necessarily two things that mix all that well. Chemistry had a bit of a bad rap from it, even up through the 20th century. And that made life a little bit interesting. Now, alchemy gets a little bit too much of a bad rap, to be honest. It wasn't the entire pursuit of finding the philosopher's stone to turn lead into gold and whatnot, although that was a thing. Its real goal was to purify what we would now think of as separation sciences. It was readily understood that there were things in this world that had effects, and that you could do stuff to it that would decrease the amount of stuff you had, but would make the effect more potent. If you think of alcohol, per se, if you have beer or wine, there's not much alcohol in it, but you can distill that down and make a distilled spirit. You can take a bunch of potatoes and turn them into vodka with a bit of work. That was understood. The understanding mechanisms weren't really there. So they didn't quite understand why doing a distillation did something different, but they were starting to get the idea, and that was really leading us towards the beginnings of chemistry. Understanding that, hey, this wine has several things in it, and if I heat it up and cool off the vapors, I get one or maybe a couple of different things, and that thing that I get from it is what makes me drunk. That's a pretty big revelation, and now you start looking for this elsewhere. Okay, so you'll notice there was a bit of a jump cut there. That's because I've had to take quite a few takes on this next part. So trying this again. Now, we were talking about the birth of chemistry and wanting to get on to the point where, boom, it's chemistry. But there is no boom, it's chemistry. Chemistry evolves from what came beforehand. So I want to talk a little bit more about the evolution of that. And I would be remiss without talking about the Persian polymaths living in the Islamic caliphates around the 8th century or so. At this time, the global center of learning was, of course, in the Middle East. Europe was undergoing the Dark Ages, which, while maybe not as dark as particularly led to believe, it still was not exactly the global center of learning during that time period. In the Islamic caliphates, a lot of research was being done. We can see the writings of Jabbar and Al-Razes, and they really start discussing modern techniques, or the beginnings of modern chemical techniques that I, as a chemist, would recognize as being my basic chemical techniques. All that old school stuff that has been, since the beginning of time, or in this case, since around the 8th century or a bit before. We usually call this alchemical because it's not really alchemy, but it's definitely going towards chemistry, but it's not really chemistry either. It's definitely in between things. It's got some of the metaphysics, but not as much, and it's really much more towards the chemistry. But really, to go into the sciences, we need the scientific method, and that is born out of the European Enlightenment, which is, shall we say, a few years later. Chemistry comes online probably a couple years really after several of the other sciences, and the usual start point, because once again, there isn't really a start point, but the usual point that we say, boom, chemistry, is the publication of the book The Skeptical Chemist. And yes, it's spelled with a Y. Things have changed in the last few hundred years. This would have been towards the latter part of the 17th century. The author, Lord Robert Boyle, was an English lord, owned a ton of land, and of course there were people far richer than him, but he was definitely very well-to-do. Now, the book itself is a discussion of alchemical ideas and basically saying the 5-element hypothesis is kind of silly. But really, the important part isn't the contents of the book per se, but how the book is structured. A few features that Boyle took ideas from other Enlightenment philosophers and brought them to chemistry. The key concept, or the key feature of the book, is that it's just written in English. It's not encrypted. It's not for an exclusive group. It's for everyone. I mean, obviously, at that time, most people, literacy wasn't exactly a universal thing. But he was being open with what he did. Intellectual property didn't really exist, or at least there was no protections for it back in the day. And as annoying as intellectual property law is, it does exist for a reason. Back then, if you discovered something really cool and you wanted to make money with it, the only way you were going to do so is to make sure you didn't tell anyone. Because the moment anyone else learned what you did, they could do it themselves. There was nothing to stop them. Today, if you discover something really cool, then the government gives you a 20 or so year monopoly on its use before then anyone else can use it, known as a patent. Well, Robert Boyle didn't really care about making a ton of money on his discoveries because he already had a ton of money. This time, science was the hobby of the rich, and hey, he was going to be open about this. He actually took this to the next level in what is really a key feature of science, at a level equal to or greater than the scientific method, and that is the idea of being able to be open enough about your research that someone else can reproduce it, the idea of reproducibility. Boyle, as well as several of the other philosophers at the time, strongly believed that the way you prove something was not simply some analogy, but you had to do an experiment, and you had to be able to communicate to others how you did that experiment, and that they had to be able to do the experiment and get the same result as you. And this is a key feature, and this is where science and chemistry become, features. Now, science at this point is still the job of the hobbyist. The rich man, very, very occasionally lady, but generally rich man at this point. And it's a hobby. Kind of nice. Robert Boyle was prolific writer, wrote heavily on theology and quite a few other items, but his money came from land, not from science. Next, we go into the 18th century with the Leblanc process. And this is a process for making washing soda. Washing soda is a calcium oxide. It's a very alkaline substance, and it's used for making soap as well as bleaching fabrics and whatnot. The Leblanc process is of particular note because it was an industrial scale. You could actually make lots of washing soda. You could have a factory that made a chemical. And during the Industrial Revolution, now all of a sudden chemistry became part of the Industrial Revolution. We were industrially manufacturing chemicals. There were significant environmental issues. The process releases hydrochloric acid as a gas, which for a while was simply left to float across the field, and that's not something you want to be downwind of. Definitely dreadful for one's health. So this was also the origin of some of the first clean air laws, etc. So a lot of things happened with this one. But chemistry is still, it's a thing, but it's still trying to shake the shackles of the alchemical past. It, once again, had a bit of a bad reputation to shake off. And then comes a guy by the name of William Perkins, probably mispronouncing his name. And at the time, he was actually like a teenager. He was younger than most college students. He was trying to make a chemical called quinine. Quinine is extracted from the bark of a tropical tree and is used to treat malaria. It's still used to treat malaria today, although there's quite a few other drugs that are generally preferred under normal applications. But at the time, it was the malaria treatment, and he was English, and, well, English men were looking for ways to improve the empire as well as make lots of money. And at that time, the British Empire was a burgeoning sea empire, if not the greatest empire on the planet. But they needed quinine because the thing that was stopping them the most wasn't other empires, it was mosquitoes and malaria. Now, Perkins knew that there were certain chemicals from coal tar. Coal tar is a byproduct of illuminating gas production. You take coal, you bake it, you get illuminating gas, which you can then send to the gas street lights and whatnot. Not what we use today. But then it leaves over this rather disgusting sludge that at the time was basically just toxic waste, had no particular value. But Perkins knew that the chemicals in coal tar were similar. Well, he didn't know chemical structures yet. That wasn't the thing yet. But he knew that they were generally similar in composition to that of quinine. So he attempted to make quinine from coal tar. He failed. But in a really good way. He didn't successfully make quinine, but he did make a purple stuff. And purple is actually a rather hard dye to get your hands on. If you're looking for a natural source of purple, a good purple dye, you're kind of limited to Tyrian purple. Tyrian purple comes from an extract of predatory sea snails that exist only off the coast of North Africa, called the murex. If that sounds like it might be something that would be a bit hard to get and a tad bit expensive, you would be right. It was called royal purple for a reason. You had to practically be royal to afford it. It was ludicrously expensive. Well, he had just made purple from toxic waste. There was money in them there hills. And at this point, we do now have some basic intellectual property protections. Now, chemistry, not only can you make a few useful chemicals, you can make chemicals that have not existed before. Mauveine, the purple substance that Perkins had manufactured, was the world's first synthetic chemical dye, and it was worth a lot of money. It became all the rage in England and throughout Europe. British postage stamps were printed in Mauveine. Queen Victoria had a dress made from it, and it was the color, because now all of a sudden you didn't have to be Queen Victoria to wear something that was purple, and even she wouldn't have worn a whole lot of purple because it was ludicrously expensive. As much as we scientists would like to talk about the goal of science being discovery of knowledge, understanding for the sake of understanding, when it comes down to it, most science is actually driven by money It's all about the Benjamins. And now all of a sudden, in the late 19th century, chemistry was shown that it could turn a profit, and that brings respectability. When, hey, you can make a lot of money working in the lab, at least a lot of money from somebody.